Hi everyone, in this video I'm going to be going through question 3a of the week 3 tutorial. So in this question we have two bivariate Gaussian distributions P and Q, and they are defined down here. So we have distribution Q here. We can see each of the distributions actually has two dimensions. So for Q we have a mean vector here, 1, 0. And we've also got our covariance matrices over here. So for Q distribution, that's this one. And obviously for distribution P, it's just on the next line down here. So what we have to do in this part of the question is compute the entropy for both of these distributions. Then we'll figure out which one is larger and we'll make a comment on why that might be the case. So actually computing the entropies, it's a pretty mechanical process. We just have to use this formula here. So I pulled this out of your lecture notes. And one other thing we'll need to know is how to calculate the determinant of a matrix, which is this calculation here. So why don't we go ahead and start filling in the values. So let's do HP first. So we start with 1 over 2. And we take the log base 2 of the determinant of the covariance matrix. That's what this thing here is. So we need to get the determinant of this one here. So we basically just have to multiply 1 by 1. That's the A times D there. And subtract 0 times 0, which is the B times C over here. So that really just comes down to 1. 1 minus 0. Okay, now we need to add D divided by 2. Now D stands for the dimension of our distributions. So D in this situation is 2. So this will be 2 divided by 2. And then we have that final log term there. So let's put log 2 pi. Okay, now log 1 evaluates to 0. So this first term we can ignore. 2 divided by 2 is equal to 1. So this turns out to just reduce down to 1 plus log 2 pi. So that is the entropy for distribution P. Let's go ahead and do the same thing for distribution Q now. Let's put a HP here. Okay, so HQ, we go ahead and do the exact same thing. 1 divided by 2, log 2, and we need the determinant of the covariance matrix for distribution Q, which is up here. So 4 times 0.04 turns out to be 0.16, and that will be minus 0. Then we go on to the second term. Q also has two dimensions, so we've got 2 divided by 2, and then that final log term there. Okay. So distribution P was easy because this first term evaluated to 0, but this one's slightly different. So using our log rules, we can change this into log 0.16 to the power of a half. I'll just write 0.5 up there. 2 divided by 2 is 1, so we'll just forget about that. And we'll put the final log term in. Cool. Now log 0.16 to the power of 0.5. Let's get rid of that power. I'm just going to get my calculator. Okay, so this is basically the square root of 0.16, and that turns out to be 0.4. So down here we can change this to log 0.4. And log 0.4 turns out to be, oops, let's get the pen. approximately 1.322. Okay, great. So we've got our entropy for both of the distributions. Let's put them side by side and have a look at them. So we'll just get rid of all the working here. So we can see that the main difference is that for distribution P, it was that first term turning into 0. So both terms have this 1 plus log 2 pi, this minus 1.3 right here. This is the difference. So obviously here, distribution P has the larger entropy. So the next part of the question is, why does P have a larger entropy? We go up and have a look at the diagram of the distributions. We can see one has this big peak. Now, we didn't actually label which distribution is which on this figure, but by having a look at the covariance matrices, we can sort of figure it out. So if we take the square root of both of the matrices, we can put the units onto the same scale. And let's just have a look at what that turns out to be. So the square root of 0.04, 0.2, and the square root of 4, well, the positive square root is 2, and we have our zeros here. Oh, this is no longer a cube. Let's just leave it like that. And obviously the other one, actually it says square root. Taking the positive roots, 1 and 1. So we can see that if we compare the specific parts of the matrices here, compared with distribution P, Q seems to have been shrunk in this dimension by 5 times. So this number 1 here, we can see that that's going to be a wider distribution. Looking at the other dimension, we have 2 and 1, we can see that it's kind of the opposite for this one. So compared to P, or compared to some distribution, this other distribution has been stretched twice or doubled. So looking at this diagram, we can see that P is probably this one that's sort of more spread out. The height of it and the width of it seem to be the same as well. So we've got 1 and 1 here. So it's more likely that P is going to be this lower one down here, which has a lower peak, but it's more spread out. And distribution Q, obviously this one that's been sort of stretched relative to the other one, it looks like it's more likely going to be this one with a big peak and sort of a compressed base, or width is probably a better way to say it. So we can see that, yeah, we think the distribution Q is this one with the bigger peak that's been compressed, and we've got to think about, like, why did we find what we found? So distribution P having a larger entropy makes sense, because with more width and a lower peak, it's sort of like saying that the probability of the outcomes for P is more spread out and therefore more uncertain. if we're looking at probability distribution Q, all of the outcomes are sort of bunched together in the middle. We can see that with the high peak. So we can be more certain about the outcomes in that distribution. At its core, an entropy is just a measure of the uncertainty of the probability distribution. So looking at the diagram here and thinking about our result, it's quite natural to see why we found what we found. The more spread out distribution actually has the higher entropy because there's more uncertainty within it.